Thank you everyone for joining us today. We have another iteration of building a ZK app in 30 minutes. We're going to cover a lot of ground today, so it's really great to have everyone here and with us. So I'm going to start presenting. Just to introduce the Aztec team that is here real quick. My name is David. I'm on the product marketing side. We have Pedro, who's going to be taking us through the demo. And then we also have Josh, who leads our DevRel team, who's here to answer any questions that you have in the chat. So we've got a lot of brain power to answer your questions. So please take notes and feel free to jump in or interrupt as well, or drop comments in the chat, and we'll get to them as we go along. Okay, cool. So thank you all again for joining. We're going to be building an app today, or at least watching Pedro build it, and you can code along, or you'll also get the recording afterwards so you can try it out yourself. We've also got many great resources on the Noir docs for you to jump into, but we're really hoping that this session today is going to give you a good introduction to what's possible and just to give you a feel for what it's like to actually build something. And so first I'm going to cover a quick intro to just ZK apps in general, the landscape, where things fit in. Then we'll dive into the live demo, and then we'll have a Q&A. So we've reached a really exciting time in the Web3 landscape. It's been a long time coming, but the application layer is finally here, I'm happy to announce. And this is all being brought to you by privacy. So we're at the very beginning of this new wave of things that can be built. But when you enable privacy and bring it into Web3, you unlock all of these incredible use cases from online gaming, where of course you don't want to see certain things on chain as you're interacting, to things like private voting, uncollateralized lending, or the entire wave of applications that bringing identity on chain privately can unlock. So quickly to recap what you might have heard about ZK, there's really two different ways that people have thought about it and worked with it so far in the space. One is, you've probably heard that it scales Ethereum. It makes it fast, cheap, and secure. And all these L2s are using it to do exactly that. The other thing you've probably heard is that it enables privacy. And so there's all these different networks that are starting to incorporate ZK in different ways to achieve different outcomes and different levels of privacy, but to try to enable people to build and incorporate privacy in their applications. But what we're going to be focusing on today is specifically not the infrastructure level, which was the previous slide, but really what you can build as developers on top of this new infrastructure, and how you can use ZK to build privacy-preserving apps. And so this is already a space that is taking off. So we have everything from identity coming on chain, like with things like ZK Passport, to things like Stealth Note that enable a glass door for Web3, where you can prove you're part of an organization and interact privately based on those credentials. Everything from that to private DeFi, email verification, and things like gaming. Battlezip is an example of that, where it's like an on-chain private battleship game. And so really the possibilities are endless with this, and we're starting to see some really exciting new use cases. Just so we're all on the same page here, we're going to cover ZK proofs just really quickly. This is probably already familiar to you, but just so we're all on the same page, what's happening here? Why are we using ZK proofs? Well, it enables one person, the prover, and Alice in this case, to prove to a verifier, Bob in this case, that she knows something, some sort of information that he can verify without her having to reveal that information. And she does that by sending him a proof that he can use to verify that. Specifically, we're going to be talking about a proving scheme, a ZK scheme that is called ZK Snarks, which you're probably also familiar with. Usually it's used just for the second property here, which is the succinctness. But we're also going to be talking more specifically here about the other properties that it enables, privacy, and of course the third one is that it's non-interactive, so there's not an extensive back and forth. Everything can just be passed in one message. So how does this actually work? Well, Alice is going to take some sort of information. She's going to feed it into a proving backend. This could be any type of backend. You might have heard of Plonk or Groth16 or different proving backends. This is going to spit out a proof, send it over to Bob, who's going to check if it's valid. He's going to do this using a verification key, which is generated during out of the proving backend during the setup. And it's importantly, it's a key that can live on chain. And so it can be stored in a smart contract on L1. And that's what we see with verifier contracts, which you'll be using today, where you're actually going to be deploying a verifier contract to continuously check if your proofs are correct. So that's a high-level theoretical overview. How is this actually being implemented? When we talk about ZK for scaling, of course, we have all of the transactions that are the witness, in this case, all the information that's coming in. And L2, like scroll, for example, will take all these transactions. And in this case, they are the prover. They're rolling all of these transactions up, creating a proof, sending it to the verifier contract on the L1 to actually verify this information. This just takes advantage of the succinctness aspect. And so it's really just trying to use layer 1 for settlement and speed, and use layer 2 to help scale transactions without having them all be on chain on layer 1. If you want to do this for privacy, you have to move the prover to the user. The user has to become the prover, and all the proofs are going to be off chain, and those are going to be sent to the layer 2 to be executed. And from there, the layer 2 is going to become the prover again and bundle all of those up and send them to layer 1. Now, you might be asking, okay, everything happens, if the proofs are being generated off-chain, you can still see how everything happens on the layer 2, like scroll, like all the wallets are public, all the transactions are public. And that's why you have something like Aztec Network that we're building, where you can have off-chain proofs, but you can also have private wallets, private transactions, and all of that is still bundled up in the same way as a ZK rollup and sent to layer 1 to be settled. So how do we actually build an application that allows us to create proofs off-chain and on the client side, and integrate them into our applications? It's been very challenging and has required a lot of advanced skill to actually build these systems and applications so far. But that's why we built Noir. It's the universal language of ZK, and it makes this super easy for you as a developer. Specifically, it allows you to use logic instead of having to write all these like crazy proofs, these crazy like circuits under the hood. Does all of that for you. And so it's a Rust-like syntax. It'll be familiar for you as a developer. It's open source, so there are many different libraries that you can use, and it's flexible. And so there's very little vendor lock-in, because you can swap out any proving backend that you choose. So if you're the world team, you might have your own proving backend that you're developing for a really tailored specific use case, but you can still use Noir on the front end. Or if you're building on Aztec, you can still use Noir on the front end, and you're going to use a proving system that is tailored to really fast client-side proofs, which is what we're trying to, which is what we're building at Aztec. So final slide here before we actually jump into the demo. This is a really great time to start learning Noir. We've had NoirCon 0 and NoirCon 1, which were 2 conferences. One was at DevCon, and then one was at ETH Denver. There was a lot of buzz around both, a lot of great attendees, and a lot of great projects that are being built and come out of those. And so the momentum is here, and it's a really exciting time to start building with Noir. congratulations, you're in the right place at the right time, and you're with the right people, with Zé Pedro, who's going to take you through actually building something now.
Hey, glad to be here. So I'm trying to show you, yeah, here. I hope you can see my screen now. Yeah, okay. Just to tell you basically what we're going to be doing here. As said, we're going to be this person, Alice, which is actually she's a fighter. She's like Brad Pitt, likes to go to fight clubs, like very very secretive and everything. But and she has to know a password in order to enter the fight club. And there's one thing, like the guy that is actually the bouncer, like that's it at the door of the fight club. He doesn't know the password, and he can't know the password as well because he's not a member. He's just a bouncer. I mean, he's just like hired to be there. And so what Alice wants to do is to prove that she knows this password, but without actually revealing it. And so the way that it works is that Alice will generate the hash of the password and will send the hash to Bob. Everyone will be able to know what the hash is because the hash is just gibberish. I mean, it's impossible to do it the other way around. You couldn't know from the hash what the password is. And so Bob can know this hash, no problem. And the way that zero knowledge works is so cool that Bob can actually verify that Alice knows the password, but without actually seeing the password. That's why it's called zero knowledge, because he knows nothing about what is the actual password. He only knows what the hash is. And so that's what we're going to be building today. So I'm Zé Pedro, and this is a little link you can follow for my link tree. And so with this link tree, which is just a link tree slash ZK Pedro, and basically you're going to see code space and cheat sheet. So let me just move to that screen. That's something else. So we're just going to present the whole window. I think that makes more sense. So I hope you can see my window now. Oh yeah, this sunny loop. Yeah, cool. So here you can see just link tree / ZK Pedro, and this is where we are going to be working. So you can actually follow along by clicking these two links. The first one is just a cheat sheet, so you can basically go here, and if you miss something in this workshop, you can always go here, and there's all the commands that we're going to be running. I mean, I think I may remember something in the middle, but yeah. In any case, this is the cheat sheet, and also the code space. So the code space, I call it for GIQ because it's really like really simple thing. So I'm gonna just present that one. Just a second, just to present something else. Yeah, just present that out. I think it's gonna be easier. So so in this, you're gonna have the sorry. Yeah, you're going to be able to choose I'm going to choose the big machine, so it's just faster to run. And this is free. Okay, right? You'll see here is paid by Aztec protocol, but it's actually paid by whoever you are logged in. So, but this is free. You have a number of hours available. And basically, CodeSpace is just a remote machine. It's like a cloud machine. But this one in particular comes with some tooling installed. So if you go on the cheat sheet and for whatever reason you don't want to use the code space, you can actually install this tooling manually. This would be the what we call Noir app and BB app. So those are installers. Those are like Rust apps, like Foundry app. So they're just like ways to get your tooling for whatever version you need. So yeah, in this case of this code space, it already comes with that, installed. So that's why it's taking a little bit, because it's actually installing our tooling. In the meantime, let's just talk a little bit about how sometimes it is a bit confusing who is actually running what we're writing here. And the answer is Alex will be writing and will be proving, but Bob will also have the same program, so he can verify. What Bob doesn't know is what we call the witness, which would be sort of like the solution to the program. So that's one thing that we should keep in mind. So once this is done, we can get started, and I'll make that clearer. So here I have what I call Nordenberg, just like a nice repo. And yeah, you can see you can actually run Nargo and BB. So Nargo is inspired from Cargo from Rust. This what it does is just it's kind of a package manager and has some tooling for executing the Noir circuits. And then BB is the Barattenberg backend. So this is what you could actually swap by some other backend as long as it understands the intermediate language between the two called ACR. So to start, we can actually just go Nargo init. And you have to define a name, gonna call it workshop. Yeah, and it creates a new program. So what we're looking here at, we have nargo.toml. So if you know Rust, it is the same thing as cargo.toml. So it has some properties. If you need dependencies, it will pull them from GitHub. And so it's just a file that you have to have. So you can understand that it's a Noir project. And then there's our main file, main.noir. So first thing we want to do here, actually, it should be highlighting the syntax. I don't know why it's not. Yeah, maybe it's still booting up. In any case, so we are Alice, right? So we want to have a password and the hash of a password. So first thing we want to do here is know how the hash of the password is, right? Because we don't know anything about that. So we need to import some kind of crypto library, some kind of library that allows us to hash things. So let's just use the Noir standard library that has it because, okay, here's the syntax. Because that's we use it a lot, obviously. So just import this hash. This is Polygon hash, very known, very ZK friendly. So let's imagine that our password is going to be 123, right? Because that's the safest password ever. And then what we want to know first of all, we want to know how does a hash look like? So we can send this hash to the verifier, in this case to Bob. So let's start there. Let's just start with hashing password. It also requires the number of things we want to hash, which is just 3. So let's just print this. So this is the first thing we want to know. Usually we'll do this in another language, but honestly, I think just fine and better to do it this way. Also, because we can introduce this this command called nargo test, and this will be show output. So it shows how does the hash look like. So the hash looks like this. Okay, here. So everyone knows this, and obviously, if you look at this, hopefully you can never understand that this is the hash of 123, right? So this is publicly known. This is what only thing that Bob will know is this hash, right? So if we are Alice, we want to have a password. Let's call it a field. Field is, I mean, I'm going to be lying, but you can treat it as a kind of a big integer. And there is the password hash. So this is what is public. Again, this will be this, right? So password hash will be something that is public, and the password will be something that only I, Alice, only I know. So the very simple circuit that we build is just, I'll take the password within my program. I am Alice, keep that in mind. I am gonna prove that if I do hash my password, it will end up matching the password hash that you are Bob. So this is what the program will do. So I will just very simply say assert hash password equals password hash. Okay. And this is it. Okay. This is my program. So you can see the program doesn't reveal anything about the password or anything about the password hash. If your program becomes too complex, you can always go and write a test and say test, and that's the test main. And let's just use the same example of a password, which is going to be 1, 2, 3, 3, and then the password hash. This will be this thing that we computed. And then you can actually check that if I pass password and I pass the password hash, that they will actually match. So I can go and run Argo test again and just see the password. What am I doing wrong here? Password hash. Oh yeah, it's I need to put that there are 3 parameters. So 2 parameters, but one was given password hash. Yes, I need to put here that it's 3 inputs. So my test has passed. So I have now actually test that my program works correctly. And I can actually even write a test that is supposed to fail. I can say test should fail. Test should fail, and I can make a test file, and I can do the exact same thing, copy it here, but then change the password or change the hash to something, just DNF here. And both tests will hopefully pass because this one is supposed to fail and it did fail. So that's good. Okay. So Noir comes with this testing framework by default that you are maybe used to work with, like with tests or basically any testing framework. So if your logic becomes too complex, you don't have to go through the whole process of creating tests in another language. Just can do it here, no problem. So let's just delete all of this and just actually prove something. So again, just to recap, we know the password. I am Alice. Only I know that the password is 1, 2, 3. You are Bob. You know the password hash. So let's just initialize. So I need to prove, right? So let's just initialize my constraint system with an Argo check. This will generate a proof.toml file. Again, remind you that this will never leave my machine, right? I'm actually going to delete this later on just to prove to you that it works as intended. So with the proof.toml, I'm going to put here the password, which will be 1, 2, 3, and the password hash that will be this thing. So by doing this, I'm actually I'm going to be able to generate a proof that I know what the password is, and the proof will it will not reveal what the password is. So to do so, I'm going to go with Nargo executes. This will basically compile my circuit into this thing, which is what we call the ACR. If you're used to Solidity, you know what an ABI is. So this is basically the same thing, just tells how many inputs are there. And then there's the bytecode, is the actual thing that's going to be built. And actually, there was the code afterwards as well. But you don't need to know what this is. It's just like it's the compiled version of this circuit. You could serve this, for example, in a form on the web or something. And here is the witness. This is what I can't open it here, but anyway, you wouldn't understand anything as well. But this is the solution of our circuit. So what Noir did was basically prove that there is a solution for this problem. There is a solution for some dark magic that will make there is a solution for the password that being hashed corresponds to the password hash. So it is not enough. I can't just give this to the prover because he wouldn't be convinced that I know the password. So I actually need this backend to generate the proof for me. So this is where PB or whatever backend comes in. So can just go PB proof. Because I've named this workshop, I can't use the default parameters, which is intended. I wanted to show you like all the flag that you can use. So you can go target workshop.json. This GZ. This is the W for witness. Then I'm sending the B for the bytecode. So target workshop.json, and also the output. So my proof goes somewhere. Okay. So this is the command I'm going to run. This will generate my proof in here. Okay. So I can't see this. There's a command in the cheat sheet you can actually use. I think it's a very last line in the cheat sheet, which is here. You can use to see the proof if you want to. So because it's a weird format, but you can see here the proof looks great. But I mean, you can look everywhere you want. You'll never see here anything that will tell you what the password is. Okay, trust me, bro. You can't. What you will see is here the beginning of it will actually be the public input. So if you see here, it ends up DD8. So this is the public input here. This is just how the backend works. This is a bit annoying, and this is actually changing. I think in the next version we'll split and show you the proof and the public inputs separately. Because like in a smart contract, you probably don't want this to be in the proof. You want this to be in the smart contract. But this is basically allows you just tells the prover what are supposed to be the public inputs. But again, this proof is a zero knowledge proof. It doesn't allow you to know what it is proving. I'm going to clean this up a little bit. Sorry, my notes are gone, just so I don't lose myself. So yeah, now we have a proof. And now I'm just going to shapeshift into Bob. I'm now Bob. I'm now Bob. Hello, nice to see you all. Glad to be here. So there's something that here I'm just going to delete everything that Alice did. Just gonna delete everything. Just gonna leave just the proof and the program. So yeah, I am Bob. I see this proof here. I don't know if it's true. I know this circuit. I know what the public input is, but I really don't know like what the password is. But Alice just sent me this proof thing, and she thinks that I can verify this proof using the same compilation of this circuit, and she can convince me that she knows the password. She knows what is this password, right? That's crazy, right? This is amazing. So let's try it. I don't know. I don't know if this is gonna work, right? I'm just a bouncer. I don't know crypto. I don't know math. So yeah, I'm just gonna compile this again, just like Alex did, I think. And just going to compile it. I have the same circuit as she has. So one thing I want to be sure is that I am actually compiling the same circuit that she is compiling, because I want to be sure that she's proving what I want her to prove. So what I need to do is generate a verification key. And this verification key will have to match the one I'm expecting. So I'm going to do that with Bratenberg. So I'm going to go write verification key and say target. This is workshop.json for the bytecode, and then the outputs. Sorry. Okay, so now I have the verification key. I can be sure that so when I run the verification, I can't, it won't be, she wouldn't be able to prove anything else other than this. I'm absolutely sure this is the circuit that she proved. So I'm good. Like, I can go DB verify, and it just works. Like, crazy, right? So now I know that given this, I know it was in the beginning, but so yeah, just knowing this, I just that simply verified that Alice knew what the password was, right? Do you see anything here that will reveal what the password is? Wrong, right? So this is really powerful. And it is even more powerful if you think that you can actually now generate a smart contract out of that. Because this is all good if you're a member of the Fight Club and you want to enter a Fight Club and there's someone that verifies your proof. But what if you want that there is no one to like no physical, no counterparty? How, right? How is it? You can generate a smart contract. You can put that smart contract in an EVM chain or any kind of blockchain, and then the smart contract will verify the proof for you. That's because the technology here is zero knowledge snarks, succinct, non-interactive arguments of knowledge. Oh, someone spoke. Okay, let me see. It's all good. So yeah, it's non-interactive. So I don't need Bob to do anything, right? I can just export this verification key into a smart contract, and then it just let the smart contract do the verification. So that's what we can do with BB. If you see BB, the help command, it will tell you that you can write the solidity verifier. So I'm gonna do that, right? Solidity verifier, and this generated a solidity verifier here out. Just make it out. That's all. And here's it. Like, this is all the math you don't want to look at. It's kind of scary. But yeah, this is all the math that goes into the honk proof, ultra honk proof. So this is what we can actually deploy in a smart contract. And I believe we still have some time, right? So we can go maybe through. So we can actually try this on Remix. So you probably know Remix IDE. You just open it and share my screen again. Here's it. Cool. So you probably know this. This is a really cool project. Come on, it opens in another window. All right, same window here. You probably know this if you are, especially if you are a Solidity developer. This is a known place to you. This is like an IDE for Solidity, for development in Solidity. So let's just start with a blank project. Create a blank project. Blank. Okay, blank. Gonna completely start anew. Just gonna paste here my file, the contract.sol. This is the contract that I just created. So yeah, it will tell you, don't paste a code snippet, don't trust. Yeah, you can, no problem in this case, just in this case. So here's my contract. I'm gonna save that, and I'm gonna compile my circuit here. This actually should, oh yeah, I should use a different, maybe 29 maybe version to compile this. Yeah, okay. So now I have my contract is compiled. Now I'm good to deploy it. So just gonna go to, whatever environment I want. Just gonna select the contract. I think it's gonna be on verifier, and I'm gonna deploy it. Right. So it will say that it is too big, and I say, yeah, no problem. You could, I could just optimize it. But in any case, like here's my thing. Here's my my verifier here. It only exposes one call, which is verify. So what I'm gonna be doing now is exporting that proof with that ugly command I sent you. Just copy it. I know you're not seeing. Just gonna show you. Just copy it to the remix window, so you know. So what I'm looking at is this proof. I'm just gonna proof whatever. So this is the huge proof that was created by Honk with the proof command. And the public inputs, you remember that it ended up with DD8. So I'm gonna split it here just to help me. So I put some 0x at the beginning. Cool. So now I have the proof and I have the public inputs. So, and I have my contract. I can deploy it. Oh, I have deployed already, so I'm good to go. I can actually now prove to my contract. I have proved to my contract that I know a password such that when hashed, it'll be the same as this thing that basically tells you nothing about the password. So I'm gonna copy my proof here. I'm gonna copy it. I'm not copying. Copy my proof into the proof here. And the public inputs, here they are. I'm gonna just say, here I think I need to quote them for public inputs, and this will hopefully prove like verify. But oh wait, file, soundtrack file. What did I do wrong? Well, I don't know. I don't know what I did wrong. But then in any case, like, yeah, it's not a demo if it works. So yeah, but this is hopefully would work and be able to prove to the contract that I know the password just by showing it the public input. Now you can basically use this in another contract to do any kind of gates that you want. And more than all, you can go into your circuit, back into your circuit, and do more complex things like proving that you are a member of a group using a Merkle membership proof. You could do things like private voting, for example, and all of that is just clever usage of encryption through zero knowledge and contracts. So again, you can just import this honk verifier in whatever contract you want and just make a call to it to verify a proof before you do something, like in a modifier or something like that. So you're gonna see some of those examples in the Noir Lang website. And that's where there are some tutorials and all of that. You can always go back into my link tree and you're gonna see the Discord. There was a Discord server. I don't know if Steve or Josh, if you can add that, like an invite there, and also noirlang.org for Okay, I see it. Noir.org for the documentation, and that's it. Yeah, it's pretty amazing. As you can see, very simple to do. Very simple, small examples, but also very simple, complex examples. Yeah, I'm up for questions if you have any.
Thanks so much, Pedro, and definitely we're happy to take any questions here. I think specifically also about what you can build with this. Maybe while we're waiting for questions too, Pedro, you could go into maybe there's some other examples you want to highlight of types of things you can build, like anything from like ZK Passport to games, or things that you think are particularly interesting to kind of get people's mind churning. But also happy to take questions here. You can raise your hand or drop them in the chat.
Yeah, definitely. Like you can think of it. It gets pretty impressive very quickly. I mean, it's already impressive, but like when you think that you can not only prove the pre-image of a hash, that also means that you could, for example, prove that a signature came from a valid public key without knowing what the public key or the signature is. And that is very nice use case for Solidity signatures. Ethereum signatures, and also for passport signatures. So you see, your passport, most passports in the world are electronic. So basically, they are signed with the key for the country. Your country signs your passport before sending it to you, and so basically, it comes with that. So basically, when you go into the automatic electronic gates in airports or something, it just reads that and signs the message, and that's basically what proves that you are in the ownership of a passport that was actually issued by the country it says it is. It also contains all the information in the passport, like your name, your age, your country of origin, stuff like that. So someone was like, how couldn't I just verify this signature within a zero-knowledge circuit? And turns out that yes, you could basically just prove that your passport was verified, was signed by a known public key that everyone knows. It's in the website, in the ICAO website, and you can prove that it was signed by that country, and then you can assert anything about what is inside the passport, like your age, without revealing any of that. So you could do things like proving that you are over a certain age, proving that you are from a certain country, proving that you are from the EU, proving that you are not from the US, or I mean, whatever you want to do, basically, as long as that information is there. And so that's really, really powerful. That's exactly what ZK Passport does. No more, no less. It's pretty impressive. So yeah, questions.
Cool. There's a question on how to get started. I dropped a link to a full stack Noir JS app in the chat. It's a great place to go and see how all the pieces fit together and just get a basic project off the ground. If you're interested also on the Aztec side, there's an Aztec starter as well. We're approaching testnet here, so it's a great time to also start learning about Aztec and how you can incorporate and start building there as well. I'll drop the link to that in the chat as well. So if you either want to get started on the Noir side or the Aztec side, there's great entry tutorials for getting started there.
Well, so there's the question, like how often can you ask for age? You can ask whatever, however you want. So I can actually show you the ZK passport. Oh no, I mean, it has my private information there, right? But it's only on my machine. So here's my ZK passport app, and for whatever reason it doesn't show my photo, so that's fine. But I can basically use this app and to prove to whoever wants to check anything about me, they could just generate a proving request. So they can say, prove that you are born after before a certain time, and I can just generate that zero-knowledge proof in my phone. So I can do it as often as you want. That's absolutely no problem. I can generate as many proofs as you want. So a ZK password moved to safe. Yes, you could do something like that, which is very, very, very interesting. And that actually comes. So I think at least one of the wallet designs for Aztec is actually to have a passport, to be able to recover your account using your passport, which is really, really cool. So you don't have to keep your seed phrase anymore. If you lose your keys, you lose your wallet, you could just use your passport to recover that and to say, I own this password, this passport, here's it, and I can recover my account. So you could do this with Safe if you want to. That's something that could be very interesting to do with Safe and Solidity, to use ZK passport. Yeah. A question that comes often is like, what is the relationship between Noir and Aztec? And this is exactly, I just touched one of them, where you can use Noir to prove ownership of a specific passport without revealing what it is, and then using that to recover your account. So that's exactly what Aztec allows. Aztec allows also for private state. So basically, you can basically, for example, send a note to someone else with some information that is private to that someone else, or it is private to you. So and basically, there is this exchange of zero knowledge proofs that doesn't even need to be on chain. But everything in Aztec is a zero knowledge circuit. If it's private, then it is run on your device, and the zero knowledge proof is not shown. And I mean, it is shown, but like not the pre-image. And if it's public, then it's like Ethereum. You just send the public input to a node, and the node will compute. The state will just generate the state, just like Ethereum does. And it's this composability, because you can have private functions calling public functions, and the other way around, with a little caveat. And this is possible. So there's this private and public composability. That's what makes Aztec truly unique. And like there was no other project that even remotely does something like this. And so Noir, the relationship between Noir and Aztec is just Noir powers Aztec. There is no Aztec if there is no Noir, or actually there is no Aztec if there is no Bratenberg. But Noir definitely makes using Bratenberg much easier than just coding the circuits in C++. So yeah, that's the relationship between the two projects. So if you are building with Noir, you're probably going to end up in a place where you would say, "Oh, this would be so cool if I could just store this value encrypted somewhere." And that's where you're going to find out about Aztec, and they're going to say, "Cool, I can actually do that, and I can have that encrypted value, and everyone can prove that it's true without being in any centralized place." So it's really, really interesting. So, more questions?
Cool. Last call for questions. You can also feel free to unmute yourself if you're able to do that, or drop your question in the chat. There's a question: any connection with ZooPass?
No. I mean, ZooPass is also zero knowledge proof. I think also zero knowledge proof, but it's just doesn't use Noir. It uses a different backend, which is based in the Grout 16 proving system. So just I was also just different. So yeah, I could definitely build ZooPass in Noir and Bratenberg, and you'll probably find it more easy to work with. But yeah, ZooPass, I think it's not written with Noir. No.
Cool. All right. We will wrap it up there. Thank you so much to Josh for answering all the questions. Thank you all for being here. Thank you to Pedro for leading the demo. It's been really wonderful. Please check out our Discord. Jump in, try out a tutorial on the docs, and follow us on Twitter at Noir or at Aztec Network if you want to stay up to date on all the other things coming up. And feel free to always reach out to our team in Discord and ask questions. We have a very active DevRel team that is always there diligently answering all of your questions. So I really encourage you to go there, check it out, drop your questions in, and let's build some stuff together.